Good afternoon, everyone. Welcome to Interaction Session 7 for NPTEL course Experimental Physics 2. The course is being taken by Professor Amar Kumar Das from IIT Kharagpur, and I am a PMRF Research Scholar Mrinalini from School of Physics, University of Hyderabad, and I am here to clear your doubts regarding every week's assignment. So, what we'll do is we'll be solving questions which will be similar to your assignment question that you have to submit this week. And if you have any doubt, you can ask me. So these sessions, as you know, we conduct every Saturday 3 to 5. And these recordings are available on YouTube. That link is also there. You will have, I think, already seen there is a Google Sheet where you get link of the drive where I upload these PPTs and link to the YouTube. Like after every these sessions, we record these sessions and these videos are also available there so that you can go through them anytime you want. Okay, so let's have a recap of what are the things we had discussed last week, which was week 6. So last week we had discussed again experiments based on spectrometer and prism. Someone's mic is on. Okay. So we had done experiment based on prism. So one experiment was measurement of angle of minimum deviation, which we had discussed. If there is no prism, then the incident light will be going following this particular path. But since there is a prism which is a different medium, because of this the incident light will undergo refraction and it will be deviated from the original path. So this is the angle of deviation that we try to measure in this particular experiment, and then based on this other many things we were able to calculate. This was like finding out refractive index and wavelength of light after we calibrate the prism. So this was another experiment. This was so what happens is this we had discussed it in detail that if we increase this angle of incidence or decrease it also, then this refraction or deviation from original path will increase. For a particular incidence angle, this will be minimum, and that is what we see here. Okay, and this angle of minimum deviation we get when the angle of incidence and angle of emergence is equal, and that time this refracted ray follows the path which is parallel to the prism base. So then we get this angle of minimum deviation. This y-axis is deviations. Depending on different incidence angle, we get different amount of angle of deviation, and the angle of minimum deviation is when incidence angle is equal to the emergence angle. So this was another experiment, and then based on this we can calibrate a prism so that we can find out, depending on how much deviation we are getting, we can find out what is the wavelength of the particular unknown light. So that this was the intention of this experiment 5th. Then this experiment 6 was about drawing dispersive curve, which is the plot between refractive index versus wavelength. So again, recalling that refractive index of any material, it depends on wavelength of the light. That's why when we send white light, which consists of 7 different lights, that means 7 different wavelengths, so they are refracted or they deviate from original path by different deviation angle. That's why when the white light comes out of the prism, we see all 7, because for all those 7 different wavelengths the refractive index of the same prism material is different, and thus their bending is different. So that's why we call that phenomena dispersion, and this refractive index as function of wavelength is, this curve is known as dispersive curve. So this was another experiment. This is dispersion, as we had discussed, when white light splits into its components when it passes through a prism. Okay, so these were the things we had discussed last week, and we had done many numerical questions as well. So now let's discuss. From this week the lectures were more about interference based phenomena and then various experiments that we do for the same phenomena. Okay, so recalling these different kind of phenomena, when we have a wave, it could be electromagnetic wave, we just call it light for our optics whenever we are dealing it in our optics lab. But for any kind of wave, principle of superposition of wave states that when two or more waves of same type are incident on same point, the resultant amplitude at that point is equal to the vector sum of amplitude of individual waves. This is principle of superposition. Now based on this we have three different types of waves. One phenomena is interference. This happens when two waves of same frequency, so frequency is same and same wavelength, but their amplitude can be different. One wave can have amplitude A, another can have A prime, and when they travel in same direction with, very important, constant, their phase difference should be constant throughout. When such two waves travel in same direction, so this is what we show. Maybe I have some diagram, maybe not, let's see. So like if I have a source and like imagine that I throw some pebble in a water body, so there will be ripple generated, right? We show it like this. And then simultaneously at another place also, like I have thrown the pebble at same time and I'm getting water ripples like this. So if they have same frequency and same wavelength, even if their amplitude is different, but if they are traveling in same direction and if they happen at some point to like they overlap or they interact like this, then we'll get something known as, this phenomenon is known as interference. So the condition here is they should have same frequency and same wavelength. And the phase difference, either their phase can be same or there can be some difference, but that difference should remain same throughout. From the beginning of that wave till the end where they are interfering, that phase difference should remain constant. So this is, then we can observe interference, that we will be discussing in detail in today's session. Another phenomena is just to discuss standing wave and beat. We had discussed in experimental physics module 1, that is last semester. We had discussed these two things in detail, but just here for recalling it and discussing. That's for standing, how interference is slightly different from the phenomena of standing wave and beat. So in standing wave, what happens is we have two waves which have same frequency and wavelength again. Their amplitude is same and they are traveling in opposite direction. So one wave is coming from this direction, another wave of same frequency, same wavelength and same amplitude is coming from opposite direction. So what happens for standing wave? If you tie a string, okay, take a string, attached one end, attach it somewhere, and then when you give it a tug or push it up, you will see something like this. Okay, if the when it will, this ripple or this disturbance reaches to the end, it comes back, and in that case you can see something like this kind of disturbance, as if like the wave is not traveling, it's just going up and down at these positions, and we get these kind of, we see these kind of points where it seems that no vibration is happening, we call them nodes, and where the displacement of particle is maximum, we call them antinodes. So what's happening here is one wave that we are giving is going in this direction, the same wave when coming back, it's coming in different direction, so they are forming this standing wave. Okay, next is beats. So when two waves of different frequency and wavelength but same amplitude and same velocity in a particular medium travel in the same direction, that time we get beat. Okay, so these are different kind of phenomena, and here we are mainly going to discuss more about interference and see how interference gives us different observation patterns. Okay, so let's do a small derivation to find out when two waves of same frequency and wavelength and they are traveling in same direction, then this interference, how it is, what is the resultant wave, what is its amplitude, what is its intensity. So let's understand that. So if I take my first wave, it's I'm representing by y1, its position and time are changing. I'm representing it like this, and it has some phase phi1. These also that we can write some harmonic motion in this form, these things as well we had discussed in experimental physics module 1, so you guys can refer those videos. So here I am directly using that, I am representing my wave by this kind of equation. Now the another wave, I'll change the subscript, again it's function of position and time, it's amplitude of the particle, and let's say for time being that the amplitude is same and it has some different phase. Okay, now the resultant wave, when these two waves which are traveling, when they interact, then what happens to the resultant wave? So resultant wave I am representing by capital Y, which will be, so we have to simply add these. Plus phi 2, and using trigonometric identity, we know 2a sine sine x plus y cos x minus y, that kind of identity is there. So using that, what we'll get is, when we'll add this, we'll get 2a sine kx minus omega t plus phi 1 plus phi 2 by 2. The derivation in detail actually has been done in the main lecture videos as well, so that will already be, I think, helpful for you. Cos phi 1 minus phi 2 by 2. So here, this, let me rearrange and rewrite, because as you can see here, this sine, this is the amplitude part, and the sine, whatever sine contains, that is not the amplitude. So here also this is not the amplitude, but the remaining 2 times a and this cos, this is the amplitude of the resultant wave. Okay, this sine kx minus omega t plus phi 1 plus phi 2 by 2, this is the phase part, and this is the amplitude of the resultant wave. And we can very clearly see that this amplitude of this resultant wave is depending on the phase difference of these two waves. This is very important, we will discuss why. So this is the amplitude, and it depends on the phase difference between these two waves, and since this is the amplitude and we know intensity, we define as square of amplitude of the wave. So intensity for this resultant wave will be square of this, which will be 4a square cos square, let's call it phi, where phi, by phi I mean phi 1 minus phi 2 by 2. So this will be the intensity. Now since this is 4a square cos square phi, and phi value can go from 0 to 360, right? That is 0 to 2 pi. Now let's see if the phi, the phase difference, goes from 0 to 2 pi, how does the intensity will change for this resultant wave. Yeah, so and then I'll tell you what this thing is. So this intensity that we just now saw, it's coming out. If the amplitude is same, that time we are taking 4a square, otherwise it will be something different. So just to simplify the mathematics here, and this phi was phi 1 minus phi 2 by 2. Okay. Now intensity I want to see as a function of this phase difference between the two waves that we were talking about. So what happens is when phi goes from 0 to further 2 pi and beyond, so when cos is 0, cos 0 is 1. If this is 1, that means intensity will be 4a square. Let's say this is 4a square. Okay, that means when the phase difference is 0, that time we will get maximum intensity. Okay, and when phi will be 90, cos 90 is 0, so intensity will be 0. Like sinusoidal, we know cos phi, so cos 0 is 1 and then it goes to negative and then positive, right? So cos, if I am plotting cos, then cos value goes from plus 1 to minus 1. But here we are taking square of it. So all these things will be positive, no negative components will be there. And because also there is 4a square constant value multiplied to this, so the amplitude increases by 4a square. So for 0 it will be maximum, then at pi by 2 it will be, intensity will be 0, then again when the angle will go to minus 180, cos pi is 1 again, so this will be 4a square. So this is how the intensity will vary, basically sinusoidal kind of, but it will never go to negative, and the values of this intensity is ranging between 0 to 4a square. Again this only when the amplitude we have taken to be same, otherwise it will be some maximum amplitude possible. So this is what I am showing here, that this bright area, bright region and then dark region, alternatively we will get when two waves are interfering. If the two waves that we are talking about, if they are monochromatic, means they have only single wavelength. Monochromatic we know means one color, one wavelength. And if it is in visible kind of wavelength it is, because we know gamma or radio waves are not, we humans cannot see them. So here if I am taking a monochromatic source, maybe this green, and those two waves are interfering, then I'll get this, as I was saying, maximum intensity I'll see, and then this region of darkness, and then again maximum intensity. So this is what I'm seeing here, that maximum amplitude, then darkness, then maximum amplitude, darkness alternatively, as we saw here. So this kind of fringe I'll see, or this kind of pattern is seen in case of monochromatic waves, and this we call fringes. This maximum amplitude and then darkness and this kind of pattern, we call it fringes. Now if our source lights were white lights which had different kind of component in it, then in that case we will not see particular light, but we will see this kind of overlapping of different components. In center you may get bright light depending on different interference pattern, but in center you may get something like this, and then you will be seeing splitting of these its components. So this usually happens in white light kind of cases, but this is also interference pattern. Okay, so this was it. Now we want to see that what is the width of these fringes. There's a darkness part and this bright or the maximum amplitude part. What is the width of these fringes in these cases? That we want to know fringe width of these interference pattern. Interference pattern. Okay. So, okay, before Young's double slit experiment, let's follow something. Also, maybe I can tell you what are the. Let me take some slides. This will be better, I think. Okay. Also, as I was saying, that this amplitude, if we are considering these two waves to have same amplitude, then we'll get something like 2a, and in intensity it will be 4a square. But if the amplitude is not almost same, or if not same, so what I want to say is, so here the amplitude was same for the two waves, so they get added and we get something like 2a times some cos of phi 1 minus phi 2 was coming into the picture, but this was there. If we have two different amplitudes, for say wave 1 amplitude is a, for wave 2 amplitude is a prime, then the maximum and minimum amplitudes will be like this, something like this. I maxima will be a plus a prime. It will get added up as if no problem, but I minimum will not be given. So if they are same, then the difference will be 0. If they are same, difference will be 0 and we will get complete darkness, kind of, you can say. Okay, we will be seeing complete darkness. But if these are not same and there is large difference between a and a prime, then what happens is the difference also will be large. Say if this is 10, if a prime is 10 times a, means amplitude of one wave is 10 times more than amplitude of another wave, then the difference will be, or whatever, don't consider the sign, the difference will be this. That means we will not be getting complete darkness. We will not be getting complete darkness. Now what happens is, here as you can see, the contrast is very good, especially when we are taking measurement. We want to see how much is the width of this fringes, the dark part, the dark part and the bright part. So we'll use spectrometer and we'll see its width. But if we are not getting this dark part, there are still a lot of amplitude of light here, then the contrast will be poor and we won't be able to observe pattern with this good resolution. Okay, that's why, although the interference will be happening and it's possible, but the thing is the contrast will not be good. That's why for interference we want the amplitude of the two waves which are eventually interfering should be of almost comparable amplitude, so that the contrast is good and we are able to observe a very good resolution interference pattern. Otherwise, taking measurement or doing some experiment with those kind of interference patterns, if they are not in good contrast, then it gets difficult. Instead of seeing complete darkness, we'll be getting some sort of light and it will be difficult to measure that till where is the bright part of the fringe. So this is one of the condition for getting good contrast, because when you will be doing experiment it should be, you should be seeing contrasting and good clear image. Okay, so now we need to see the condition for, yeah, as I was saying, we need to see the fringe width. So let's see how we get that. So when we have a source, okay, wait, what's happening? If I have a source S1, let's call it S1, and another source S2, which we are talking about their interference. So this is source 1, and that interference I want to observe on a screen. This is my screen. On this screen, that pattern I am telling you about, these kind of patterns we see on the screen after the two sources interfere. Show interference, and then the pattern, resultant pattern, we'll observe here. The like bright and dark kind of pattern will happen here, depending on where these two waves are interfering. Like what I want to say is, if I consider the middle of these two point source, if this is the midpoint, this is the wave traveling in towards front, this is also, then if they are just going in this direction, then there will be no interference. For interference, they need to be in contact with each other. But we know any source of light, until something like we make something known as laser. That's why laser are special type of lights which only mostly go in one direction. That's why we use laser lights for pointing, right? Otherwise, if we are just talking about any normal like bulb kind of light emitting source, then it emits light in all the directions. So it is a source, but it's emitting light in all directions. It's not a point source, but kind of it is a source, and it's emitting light in all the possible directions. Same way, if I'm taking a light source here, it won't only be, the light emitted from it won't only be traveling in one direction, it will be traveling in various directions. Something will be going in this direction, something will be going in this direction, all these directions will be the waves will be traveling. And when the wave from S1 interferes with the wave from S2 at this point, and there are certain conditions which it needs to follow. If it follows those conditions, we'll be seeing interference pattern as a result. Not only here, if some part of this reaches here, and there is one light going in this direction, if they follow the sufficient interference condition, we'll see interference pattern here or in between also. So wherever they'll follow, so what ultimately happens, because of this interference pattern is here, because of here interference pattern is here, there will be a lot of interference patterns which will be overlapping. So sometimes that also happens. That's why we try to avoid getting these many interference patterns together. Otherwise, these interference patterns will be overlapping and we won't be able to see a clear contrast pattern for our experiment or measurement. So what we try to do is, we keep a slit so that we don't get in all so many directions. And if here is my source, then I'll be getting a wavefront or this wave in one particular direction. So this is not all direction, so that we can avoid that. Okay, so taking this forward, if I have a source S1 again, like this, and source S2, and this is my screen. One light is going here, another wave, let's say, is interfering it here, and the distance between these two sources is, let's say, denoted by small d. The wave, this path, okay, the distance between this is in same vertical plane or horizontal plane, my both sources. Okay, so the distance between this screen and the sources, this is same for both S2 and S1 sources, and I'm calling it capital D, represented denoting it by capital D. But as I said, some will be traveling even when we are using pinhole or some kind of slit. We are not able to make it completely go in particular direction. It will be diffract through. Sorry, even if I have something like this, the light will bend. We know diffraction, and it will be going in slightly different direction than from the straight path. So some light will be going in this direction, and what happens is, although the distance between the screen is capital D, since it's going along different, there will be the path S1 wave is covering and the S2 emitted wave is covering. You can clearly see this is more path, this is smaller path. That means there is path difference between these two. When they are reaching this point, let's call it capital R, when they are reaching point capital R on the screen, there is a path difference. When I'll drop this perpendicular from S1, let this point be capital P, when we'll drop this perpendicular, so this path S1R and PR are same, but this is the extra path that S2 emitted wave is traveling to reach the point R for interference. Okay, so this is the extra path, or that we call path difference between these two waves. Now let's take the center of these two sources and let's call it as the center. From this center and where that particular whatever would be happening here, they are reaching, either they will be doing constructive interference or destructive interference, means either we will be getting darkness or brightness, and then there will be other lights reaching subsequently. So that particular fringe that we will be getting here, its distance from the center is, let's denote as by x. Now since the path is, there is some path difference for this particular wave, so there will be extra phase difference also. Although S1 was traveling with some particular phase phi1, and S2 was traveling with some phase, like from here it will be traveling straight, it was going with some phase phi2, but when it's going in this direction, and maybe their phase were constant whenever they were traveling straight path, but when it reaching here, because of this path difference, there will be some extra phase difference as well between this phi1 and phi2. So initially when they will be traveling in straight path, the phase difference maybe was only phi1 minus phi2, but now when they are traveling in this particular path, the phase difference will be for phase difference for S2 wave will be phi2, which it initially had, and then the remaining will be because of the path it's traveling. That is given by 2 pi by lambda times the path difference. This is the extra phase difference that is getting induced. Okay, and this is 2 pi by lambda times the path difference, which is this S2p, this path. Okay, so this is the extra phase difference coming for the second source of wave. So the phase difference now will be phase difference when the time these two waves reach point R on screen, that phase difference will be this total phase for S2, which is phi2 plus 2 pi by lambda multiplied by S2p, and we'll subtract from this the phase of phi 1. If this is straight line, then it will be simply phi 1. If it is also going away like this, then it will be something little more. But just consider that this is just going in straight line, S1, and this one is going away from the straight path. So this will be phi 1. So this difference will give us the phase difference here. Okay. So now what happens is, for intensity we have seen cos can take values depending on the values, or phi takes, cos can vary between 0 and 1. So if cos square phi is 0, we get dark fringe. And when do we get cos to be 0? When phi is like pi by 2 or 3 pi by 2 and so on, right? That means in general, if I want to write like odd multiple of pi by 2, when phi is odd multiple of pi by 2, we are getting cos phi to be 0. So if in general I'll write that this condition, that when cos square is giving me dark fringe, when the phi, that is the phase difference, this phi is not the angle, keep in mind, it's the phase difference we are talking about. So when the phase difference is odd multiple, right, whatever value you will keep here, you will get a odd number. So when it is odd multiple of pi by 2, that time we are getting these dark fringes. Another condition is this cos square phi is giving the maximum amplitude. Maximum value cos square can give is 1, and we get 1 when phi is either 0 or pi, 2 pi. So values like this. That means when phi is there is no odd, it's just a multiple of pi, where n is 0 plus minus 1 plus minus 2 and so on. So this is the situation when we will get the bright fringes. This is the condition for bright fringes. Okay, now from here again, so here this S2P, and if I join this, and in this right angle triangle, okay, S1P S2 in right angle triangle, okay, I just need one. In right angle triangle S1P S2, S1P S2, okay, when I take sine theta, it will be sine, then I forgot to tell it, angle here, if I call theta this, then this angle will also be theta, and if I am taking sine theta in this triangle, then it will be S2P by this small d, right, perpendicular upon hypotenuse. So S2P by d. Now what happens, if this theta is small enough, then we can equate it to be equal to tan theta as well, and tan theta, we can see tan theta is perpendicular upon base. So this is perpendicular and the base is, sorry, wait, I made a mistake. Okay, yeah, that's fine. So we can equate it to be equal to this, and this will be x upon capital D. Okay, in this, so we'll get this. From this we can say S2P is X. We can equate sine theta and equal to tan theta if the angles are small, which they are most of the time in this kind of interference patterns when we get. So here we get S2P is X times small d divided by capital D. So this is the, and we know S2P was our path difference. So we have obtained path difference in terms of what is X, D and D. This capital D is the distance between the sources and the screen. This small d is the distance between the two sources, right? And this X is the distance from the center to where that particular fringe we are talking about, distance of that fringe. So in terms of these parameters, we will be able to get the path difference. Now, okay, we can talk about Young's experiment. From that also, there also actually we talk about, but okay. Before that, let's find out what is the formula for dark, bright fringe width and dark fringe width. Yeah, so what I'll do here. For nth bright fringe, we are not particularly saying first or second, we are just saying for some nth bright fringe, the path difference as we saw here was xd by d. So that x, which is the distance from the center to that particular fringe, if we are talking about first, then it will be 1x. If we are talking about nth fringe, then it will be n times x. So it will be that, let's call the distance xn, okay, multiplied by d by capital D. This is the path difference formula that we just now derived. So that will be the path difference, and it will be for bright fringe if we are talking about, because just here we saw for bright fringes the phase difference should be n times pi. So here also, if you are talking about bright fringe, then this path difference would be n lambda. Okay. Now for n plus 1th bright fringe, the path difference will be x n plus 1 times d divided by capital D equal to n plus 1 times lambda. So if this is the bright fringe is occurring, its position is at n lambda, and for the next bright fringe it is given by this relation, then if I'll take the difference between these two, then I will get the width. What I'm saying is, if I'm getting a fringe, say dark fringe or bright fringes here, then there will be dark fringe, and then again there will be bright fringe here. If xn means this position of bright fringe and xn plus 1 is this position of bright fringe, then if I subtract these two positions, xn minus xn plus 1 and xn, then I'll get this width. If I subtract the position of these two, then I'll get the distance between these two, which will tell me the width of this dark fringe or bright fringe. Okay, so bright fringe width bright fringe width will be given by xn plus 1 minus xn, which will be equal to, if you see from here, xn will be n lambda times capital D divided by small d, and from here we'll get xn plus 1 is equal to n plus 1 times lambda times capital D divided by small d. Okay. For this difference in position, we'll get n plus 1 times lambda times capital D divided by small d minus n lambda times capital D divided by this small d. So I'll get here two terms, n lambda d and lambda d. So n lambda d by d will cancel and I'll be left with lambda times d divided by d. So the fringe width for bright fringe will be lambda times capital D times small d. This will be the fringe width. Usually we denote fringe width with beta. So the fringe width for bright fringe will be given by this formula. Similarly, if we are talking about dark fringe, if we are talking about dark fringes, then for again nth dark fringe, path difference xn times d, but now it's just, it will be odd multiple of lambda by 2, and so this, I hope you know that the relation is something like phase difference is 2 pi by lambda of path difference. So phase difference, if n pi, then path difference will be n pi cancel, n lambda by 2. Okay, this will be the path difference. So this is the relation between phase difference and path difference. So using this relation between phase difference, we are using it here for, we are using it here for path difference. Okay. So for dark fringes, for nth dark fringe, the path difference will be like this. Now next, for n plus 1th dark fringe, the path difference will give xn plus 1 d divided by capital D to n plus 3 times lambda by 2, the next, right? And hence the width of this dark fringe again will be the difference between the position of this xn plus 1 minus xn, which would be, to see this, 2n plus 1 times, okay, let me write here, 2n plus 1 times lambda by 2 times capital D by small d minus 2n, oh sorry, this will be this first and then this one, 2n plus 1 times lambda by 2 capital D divided by small d. So when we will subtract this 2n lambda by 2 d by d, 2n lambda by 2 d by d, this is the common term, this is the same term, so it will get cancelled and we will be left with, okay, what's that, right? Okay, 3 lambda by 2 capital D by small d, this minus lambda by 2 capital D by small d. So 3 minus 1, that means 2 by 2 lambda d by small d. So this will be lambda times capital D divided by small d. So this, as you have seen, the fringe width for bright fringe also was lambda d by d, and for dark fringe as well it is lambda d by d. That means the fringe widths are same for both bright part of the pattern and dark part of the pattern. So, and this is the formula that we will be using to find out fringe widths in various numericals that we are going to do. Okay, from here comes this Young's double slit experiment, where basically what we want to do, okay, so there's something called coherent source. Okay, let me take more slides. So when we are talking about interference and how to get two waves to interfere to obtain that particular patterns of fringes, dark and bright fringes, here first condition I had told that to get good contrast, the amplitude of the two waves should be almost same to get good contrast interference pattern. Now here there is another thing is, as we were saying, interference happens when the frequency or wavelength of the two waves is almost same. So to get this kind of source, it's difficult if we have two independent sources. If we have two independent sources, it is difficult to have exactly same frequency and wavelength of those two independent sources of wavelengths, sources of light. So in this situation, what we usually do is we take one single source of light or wave, and then from this source we try to get interference. One would be direct wave coming from that source, and one would be its reflection, or we'll see there are various ways which we try, but we go for using the same, like that single source, and get two sources out of it, so that we'll be able to get exactly same frequency and wavelength out of it. Another thing is, we call this coherent sources. And we need coherent sources to get interference pattern, and we call coherent sources when the frequency is same and their wavelength is same and the phase difference between those two sources is constant. So phase difference is not zero, the phase is not same, but the phase difference is constant, and this is the condition we need to get interference as well. Okay, so this, keep in mind, we'll be seeing by various means how we can get something like that, so that we get coherent sources for our experiments or for different kind of interference patterns. So Young's double slit experiment is first of in this direction, where what we do is we are using this single monochromatic source of light. We have a slit like this which has a small hole through which this light will come, and there will be some bending of this wave, that's why it won't be only going in one direction. So this kind of wavefront we talk about. Either we talk about in ray optics by lines, or we talk about wavefronts, waves, right? So this is one source, and the wave coming out from it like a ripple is in this much direction. If I keep another slit here with two holes in it, then this wavefront, when it will pass through these holes, these two holes will behave as independent sources, as if they are the emitters of these waves. I hope you understood that actually we are using single source of this wave or light, and at some distance we are keeping another screen or some kind of barrier which has two holes in it, S1, S2 as shown here. And when this wavefront or this wave which is coming out from S will pass through S1 and S2, they will have they will be like, this is S1 source, this is S2 source. They will behave like independent sources of lights, but the good thing is because they are obtained from the same source, they will be exactly of same frequency and wavelengths. Okay, and their phases will also be same. And of course, if I'm taking the interference at this point, point P, then since their path they are traveling is different, there will be some phase difference and we'll be getting interference pattern. So this is one way of getting coherent sources for our interference patterns. Okay, so this is done by a scientist with name Young. That's why it's called Young's double slit experiment, because we have double slits here through which this single source, when is passing, it's behaving as if we have two different sources of light. Yeah, so again, why we had done this? Because otherwise, if we actually are using two independent sources of light, then it's difficult to get the same frequency and wavelength. So that's why we are using this particular method. This here also is showing same. These two sources. If you say S1, S2, then they will interfere and we'll get this absence of color, so dark and bright, dark and bright. This will eventually interfere and give us these kind of patterns. Okay, so if there is some derivation, let me see. No, I think we can continue with this. Okay, so now let's understand, after Young's double slit experiment, there is something known as Fresnel's biprism. So as the name biprism tells us, we are talking about two prisms together. So when we were talking about scattering or dispersion phenomena particularly, we were talking about a prism made up of some sort of glass material, and when white light passes through it, it undergoes refraction first at this interface, then at this interface, and it deviates from its original path and it scatters in different components and we get dispersion. So this was a part of the prism we were seeing. We were calling this angle between these two refracting surfaces, we were calling it angle of prism, capital A, or refractive angle of prism, because it's the angle between two refractive sides. So here, what we are doing is we are combining two prisms like this. This is one prism, but here interesting thing is this is very, like here maybe these two angles were same. Here what we are doing, this is called base angle of the prism. Okay, what happened? Yeah, this is called base angle of prism. This is the base of this prism, and the angle opposite to it is what we are calling base angle, and it's very small angle. And when this another same kind of prism when we take and when we combine these two by bases, and this angle is very large, around like you can say 178 degree or something, and these two angles are very small, sometimes 0.5 degree each or 1 degree each, these two angles. So the total it's like 180 degree, of course, but this is large, these are very small. This kind of combination of two prism give us biprism. Okay, so this same biprism, Fresnel's biprism, when we use, so this also gives us two we can say two independent sources of waves or lights, which will give us interference pattern. Again, how do we do? Like how do we get it? Using single source. So if I have a single source S, now light from the source, and this is my Fresnel's biprism kept here. Now light from this source, it will be going in all the possible directions. Let's consider this. If one ray is going in this direction, it will refract and pass, and the emergent ray will be in this direction. If I'll extend it back, then it will reach somewhere S1. Same way, if I consider it going to this remaining half part of the prism, some ray is going from here, and after refraction it's reaching the screen at this particular point. If I extend this also, and then the center one which is going straight, it's reaching O. So when I extend, or it's reaching in this direction, so all this when I extend it, this will go here and it will come out here, this will go here, and I think it will come out this. So when we extend these at the back, these two will seem to be coming out from S1 source, and these two will seem to be coming out from the source S2. So these are the virtual sources or virtual points, you can say, that although the source is here, after refraction the wave is coming out such, like it seems they are coming out from points S1 and S2. So what we have done is, from single source S, we have got the waves coming here as if they are coming from two independent sources. So they will be coherent in nature because they are coming from single source, and then we'll be able to get the interference pattern. So this is another way. Apart from this double slit, they can use biprism to get interference. Now there, as apart from biprism, Fresnel's double mirror also there, which also gives us coherent sources of waves. Now here what happens is, so we have mirror arrangement like this. Two mirrors kept at some angle. So this is polished side of the mirror. So our opposite side is reflecting. This is also polished side of the mirror. So this side is reflecting, and they are kept at some angle with each other. Let's call that angle theta. This is mirror M1. This is mirror M2, kept at angle theta with each other. So here, if I have a source S, when it will reflect from mirror N1, this one particular ray, it will, if I make a normal to this mirror, let's say this is incidence angle, then this will be reflection angle of reflection. So following that law of reflection, whatever the ray is coming from the source, it will reflect from the mirror M1 and reach, this is my screen, it's reaching it at this point. Now from the same source, it will be again in various direction. So one ray we are considering which is reaching M2 mirror, and if I draw a normal to M2 mirror, then this is angle of incidence and this is angle of reflection. Now this, again after reflection, it will reach this point. Now since we know plane mirrors form virtual images, so it's like it's coming from this is the object and its image, it's like coming from here. If when we extend this point, we'll see that it's coming from S1, and when we extend these points, it seems like it's coming from S2. So again, using single source, we are obtaining the waves that we are getting after reflection. It seems their behavior is like they are coming from two independent sources, and thus they will be coherent and they will be giving interference pattern, and the distance between them is being shown d. Okay, and then the other fringe width formula will remain same, which is the distance between screen and these two virtual sources, and divided by small d, which is the distance between these two sources, and the wavelength of light, which is same, right, because we are using coherent source. So this was another way. After this, yeah, we have Lloyd's mirror as well. So okay, so till now the methods that we were discussing, okay. Young's double slit experiment, or wait a minute. Yeah, so the cases we were discussing, like this Young's double slit experiment, Fresnel's biprism, Fresnel's double mirror. In this, what was happening is, when the, we can see here better I think, or even here it's fine, that at the center, right, we are, this position of the fringe we take from the center. That center is between the midpoint of these two sources, source position. So the position of fringe from the center we are taking, and at the center, okay, the fringe, because the path followed by the wave coming from these two sources, the path traveled will be same. That's why at the center the phase difference will be 0, and because the path difference between these two will be 0, so phase difference also will be 0, and thus at the center we'll get bright fringe because the phase difference is 0. Okay, for this double slit experiment also, for Fresnel's biprism also, if you see at the center the path difference traveled will be same, phase difference will be same, and we will be getting bright fringe. For this, the same will happen for Fresnel's double mirror also. So we have this another method which is using Lloyd's mirror, where at the center, instead of getting bright fringe, we get dark fringe. Okay. So yeah, as I was saying, unlike all previous cases, here the center fringe or 0th order fringe will be dark fringe. Okay, why this happens is, this is a plane mirror, this is a source, single source again. Now we have a screen kept here. Again, the distance between screen and source we'll consider capital D. So what is happening from this source, one part of wave, or one wave I am considering interference between two we are taking. So one wave I am getting directly from the source on the screen, this one. Okay, this is direct from source, it's coming. Another wave will be, so lot of it will be reflecting from this plane, like this one. These all are going and reflecting. So what happens is, after reflection, since this is air and this glass is some denser medium, it is glass, and of course we know it's optically denser than air. So when these waves which are reflecting from this, when they reach this point, they get phase difference of pi. Phase difference of pi gets induced in those waves because they are reflecting from a denser medium. Okay, this is known to happen, and because the phase difference is pi, so path difference will be, we know phase difference is 2 pi by lambda times path difference. So path difference will be lambda times 2 pi times phase difference. So if phase difference is pi, that means path difference is lambda, right? So it's lambda by 2. That's why. So path difference will be lambda by 2. So here the two waves which are interfering, again they are coming from same source. so there is no issue. They can be called coherent sources, but one is directly coming to the screen, another is coming after reflection from this mirror. That's why it will have some path difference or some phase difference, unlike these cases where when these two waves were reaching the center, they had zero phase difference, zero path difference, since they were traveling same path, same path distance. So we were getting center fringe bright. But here for Lloyd's mirror, since some phase difference is getting induced after reflection from a denser medium, so the center fringe will become dark. But again, for this particular Lloyd mirror situation, what happens is, if mirror is of this length, then the extreme light reflection that we can get is here, right? And this another side, the extreme we can get is here. Oops. That means what I'm trying to say is, if length of mirror is from here to here, this is the size of mirror, then from this source the light is going in all direction, all possible direction, but the one which are reflecting, the nearest one is this, it's going here, the farthest one is here. So we can only see the fringes and the interference pattern between this and this one, wherever it is going. So only between this region. So we won't be able to observe this, but this is how it happens. Okay. So this is Lloyd's mirror. Now there were other different kind of things related with these splitting of amplitude are there, that I think when we will be, because these, based on this, we can discuss about Newton's ring and Michelson interferometer. So I think those experiments, when they'll come, we'll be discussing them in detail. I think now, since we have 1 hour left, I think we should start with discussing the numericals based on this. Yeah, there was one experiment also based on Fresnel's biprism, which is measurement of wavelength of monochromatic light. That how we can do, just to understand the theory behind it. Since we know fringe width depends on distance between screen and source, distance between the two sources of light, and multiplied by the wavelength of light. Since coherent source, of course, wavelength is same. So when we use spectrometer and we have biprism kept there, and then this interference pattern we see, then using our spectrometer and the scale, Vernier scale there, we can measure beta. Once we will kept our eyepiece at one position, then another position, then the difference between them will give us beta. Capital D is known, small d is known. Thus from this relation we will be able to find out the wavelength. Okay, so this was the experiment, and the demonstration is available in this week's lecture. There you can go and see. So let's now start discussing various numericals based on this fringe width and Young's double slit experiment kind of topics that we have discussed. Okay, so the first question is, the width of the two slits in Young's double slit experiment are in the ratio 9:25, width of two slits. So we know one is source, whatever wave is coming from here, we have this starts behaving as when this wave passes through these two, they start behaving like independent sources, S1, S2. So the question is saying that width of these two slits are in the ratio, let's call this width W1, this width W2, and then the ratio, their ratio is 9:25. Okay. Find the ratio of intensity of maximum to intensity of minimum in the interference pattern. So intensity we know is proportional to, it's equal to square of amplitude. And here we have been given width ratio and we have to find out ratio of intensity of maximum to minimum intensity. That means we have been asked to calculate ratio of maximum intensity to ratio of minimum intensity. And since we know intensity is square of amplitude, that means this is maximum amplitude divided by minimum amplitude and square of it. Okay, now how to get this maximum amplitude and minimum amplitude? So we have one more thing given here. Assume amplitude of light coming from slit is proportional to the slit width. What does it mean? We have to consider here that amplitude of light coming out of these two slits is proportional to the width of the slit. That means amplitude of S1 source, the light wave coming from S1 source, amplitude of that one will be proportional to width of slit S1, and amplitude of second source of wave will be proportional to the width of second source slit. That means the ratio A1 by A2 will be equal to W by W2, and since we know the relation between intensity and amplitude, we will be able to find this, which will be, so the ratio of I max to I minimum will be this, so A maximum and A minimum. Okay. So how this happens, as we were saying, we had seen in the very beginning when we were deriving that if we have same source, then we can simply add and get 2A and they can subtract and give 0, because A maximum will be A1 plus A2. Okay. A minimum will be difference of these two, which is A1 minus A2. So maximum amplitude can be A1 plus A2, minimum can be A1 minus A2, and that's why we are talking about, for contrast, these amplitudes should be almost same. Okay, so based on this, the A maximum will be A1 plus A2. A minimum will be A1 minus A2, square of these. Yeah. Now how we'll get A1 A2? From this relation you can see A1 is W1 divided by W2 times A2, and actually we have been given this W1 W2 ratio, so I can directly insert it here, 9 by 25 times A2. Yeah, when I put this here, okay, or there is some, if width, the relation between amplitude and width, just a minute, I'm doing a mistake. A1 and A2, 9 by 25. So it will be 9 by 25 A2 plus A2. Let me write. Let me take. So I max by I minimum. I max by I minimum is 9 by 25 times A2 with plus A2 plus A2 divided by 9 by 25 times A2 minus A2. and square of this means square of everything. So this will be 25 plus 9 is 34, and here it will be 25 minus 9 is 16, and a2 will cancel. So when we will solve this, it will be 16. Okay. I'm wondering if we made some mistake here in understanding some part. This is not correct. So the square of 7. Even if I take square, it's 289. 64. I think, where did we do the mistake? So W1, W2 is given to be 9 by 25. Ratio of intensity, amplitude of light coming from slit is proportional to line width. Intensity we know is proportional to amplitude. Let us do this again. Okay, this is not coming out to be correct. Let's do it in a simpler way. That we have been given width, concepts are same, only while solving I think I made some mistake. So if we have the width ratio to be 9 is to 25 like this, and intensity we know is proportional to amplitude square, that means, and amplitude we have been given this way, implies intensity is proportional to the width square, right? So if I consider intensity from first source and second source, right, then I can take it to be this, and this is proportional to this. Okay. From this we will get I1 by I2 is equal to A1 square by A2 square. So A1 by A2 will become, which is square of W1 and W2. So A1 by A2 will be 3 by 5, square root of 9 by 25. So A1 will be 3 by 5 A2. Okay, if this is the relation, then maximum intensity to minimum intensity ratio, it will be A1 plus A2 square divided by A1 minus A2 modulus square, which will give us 3 by 5 plus 1, 3 by 5 minus 1, and A2 square will be cancelled, and this will give 8 by 5 or 2 by 5 square. 5 will be gone. This will be 8 by 2 times 8 by 2, 2, 4. It was 60. For me, it's 4 is 16. Yeah, 4 was 16 actually. Yeah, so it will be 16 by 1. So the ratio we are getting is 16 by 1. Yeah, I think we made some mistake. Yes, the ratio will come to be this. Yeah, 16 by 1. we can try like this again. Maybe one of you can see what was wrong here. But this is another way that which we can find it easily. Okay. So the next question is green light of wavelength 5100 angstrom from narrow slit is incident on a double slit. This is the case of double slit experiment. This is green light source of wavelength 5100 angstrom. When it passes from this double slit, it's incident on this double slit. If overall separation of 10 fringes on screen is 2 centimeter, this is my screen, and overall separation of 10 fringes on screen is 2 centimeter. Find the slit separation. Slit separation means the distance between these two sources, S1 and S2 sources. Separation between slit and screen is 200 centimeter. That is, this is our capital D, and wherever the pattern is forming, this is our center, and we have been given wavelength. Okay, now we know our fringe width formula. It depends on this distance between screen and source. It depends on distance between sources and the wavelength. So here, how we'll obtain the fringe width? We have been given the overall separation of 10 fringes on the screen is 2 centimeter. Means these 10 fringes are covering the area of 2 centimeter on the screen. Means fringe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, whatever is forming on the screen, they are taking the distance or covering the distance of 2 centimeter. That means one fringe, because we know the fringe width is same, especially in Young's double slit experiment, the fringe widths are same for dark and bright fringe. That means if 10 fringes are covering distance of 2 centimeter, that means 10 fringes are covering distance of 2 centimeter. That means one fringe will get 2 by 10 centimeter. That is 0.2 centimeter is the fringe width. Okay, that means we know beta. Now we have to find out this small d, right? We have to find out slit separation. The small d will be this capital D times lambda divided by beta. D we know 200 centimeter. Lambda is 5100 angstrom. When I'll change angstrom to centimeter, because all our answers are in centimeter, so angstrom is 10 to the power minus 10 meters. 1 angstrom is 10 to the power minus 10 meters, and in centimeter it will be 10 to the power minus 8 centimeter. Yeah. So 5100 10 to the power minus 8 centimeter. This is the wavelength. This is wavelength, and beta is 0.2 centimeter. Okay, so using calculator, when I will calculate this part, I'll get 200 times 5100 divided by 0.2. It's 51 and 2, 3, 4, 5 zeros, and we have this part also, 10 to the power minus 8. That means finally it will be 51 times 10 to the power minus 3 centimeters. If I write it in decimal like this, it will be 0.051 centimeter. So our answer is option C. 0.051 centimeter is the slit separation for this particular question. Next question is, in a Young's double slit experiment, the obtained fringe width is 0.6 mm. So fringe width is 0.6 millimeter. when the wavelength of light is 4800 angstrom. If the distance between the screen and slit is reduced to half, what should be the wavelength of light used to obtain the fringe width of 0.45 mm? Okay, so there are two different situations here. Let's first consider case 1, where the fringe width is 0.6 mm and the wavelength we are using, I think wavelength of light is same for both conditions. Wavelength is this. And in case 2, for case 2, the things given are lambda is same, we are using the same source. Only thing we know here if the distance between screen and slit was capital D, here that thing is reduced to half. Earlier if the distance between screen and the slits was D, now it's reduced to half. Okay, this is the change. And now we want to find out what should be the wavelength of light used. Okay, so wavelength will also change here. And we need to find out what should be the wavelength of light used. This is not this. We need to find out what is the wavelength of light we should use to obtain fringe width of. Okay, fringe width we know in this condition, which is 0.45 mm. So for the first case, when the distance was D and we were using 4800 angstrom wavelength, then we were getting fringe width of 0.6 millimeter. Now if I reduce the screen and slit distance by half, and what we are getting is the fringe width has reduced to 0.45 mm, then what kind of wavelength we should be using so that we get fringe width like this. So first let's apply our formula for case 1. We know fringe width is given by this formula. For case 1, when I'll apply this, I'll get beta is 0.6, capital D we don't know, lambda we know, right? And this is in angstrom. My answers are also in angstrom, so okay, let me see. This is in 0.6 millimeter. So 0.6 millimeter, let me make it 0.6 millimeter. 0.6 millimeter, let me write it here. Okay, this is an angstrom, and small d, that is the distance between these two slits. I think that has not been given to us. This is for case 1. For case 2, when I apply this formula, the fringe width is 0.45 mm. This I should change in some common, either I'll change angstrom to millimeter, but my final answer is an angstrom, but still okay. Angstrom, if I change to millimeter, 1 angstrom is 10 to the power minus 8 centimeter, right? That means in millimeter will be 10 to the power minus 7 millimeter. 10 to the power minus 7. Okay. So here also, now the D is changed to half, and the wavelength we don't know, and small d I can find out from here actually. No, maybe not. Okay. Small d is still same. So if let's call it equation 1, let's call this equation 2, because there are two unknown parameters, capital D and small d. So I cannot use the substitution method. So what I'll do is I'll divide equation 1 by equation 2. No, I need one. So when I'll divide equation 1 by equation 2, I'll get 0.6 divided by 0.45 right? And on right hand side it will be d times 4800 times 10 to the power minus 7 divided by d by 2 lambda, d lambda by 2 minus this small d. This divided by this means small d will be cancelled and we will be left by d by 2 lambda. Again here this capital D also will be cancelled and we will be left with 2 times 4800 into 10 to the power minus 7 divided by lambda. Now we have only single unknown parameter, so now we can find out the wavelength. 0.6 divided by 0.45 will be 0.6 divided by 0.45. This will be 0.27. Now when I'll take this all in the denominator, this side it will be 2 times 4800. 9600 times 10 to the power minus 7 is equal to 1 over lambda. That means lambda will be 9600 times 10 to the power minus 7 divided by 0.27, which will give 9600 divided by 0.27. 35, something like this, times 10 to the power minus 7. So in angstroms, there was this 48 would be 96 and it will come down. This is lambda by 2, it went there and became 2. Just okay, again what is going wrong here? This okay. Where is it going on? 0.6 is this, 0.45, then D multiplied by 4800. Small d's will be cancelled and we will be left with d by 2 lambda. Then this 2 will come up. 0.6, let me again check if this is correct. 0.6 divided, 0.6 divided by 0.45. Okay, this I made a mistake. This is 1.3333. When I'll divide this, it will be this, and then when I'll take this in denominator, so 1.3333 and 600 divided by 1.33, it will be mistake. It will be 7200 some values and 10 to the power minus 7. If I want to keep it in form of angstroms, then it will be, right now this is in millimeter. Now, so 1 angstrom was 10 to the power minus 7 mm. So 1 millimeter will be 10 to the power 7 angstrom. So this will be 7200 0.18 angstrom, and the matching answer here that we see is the C. If we ignore the decimal, the 7200 angstrom is the answer here. Okay. Now question number 4. A double slit is illuminated by a light of wavelength 6000 angstrom. So we have a light of wavelength 6000 angstrom, and we are doing here double slit experiment. Okay. Calculate the angular position of 10th order maxima in radians from its central maximum. So again we'll have two sources. This will be screen. Somewhere they are reaching and interfering, and from the center the distance is this. These things are like this. Okay, so we need to find out. Okay, slit separation is given. Slit separation is 1 millimeter, and we have to consider angular position to be very small. This also we need to consider in mind. And wavelength is 6000 angstrom. Now the angular position to be very small. Angular position means this is very small. Okay, now this is S1, this is S2, this is some point R, this is the center O. Then in this particular triangle, or if I call this P, this particular triangle, if the angle is very small, then we can take tan theta to be x1. First tan theta will be this x10, if I call it, because 10th order maxima we are looking for, so 10th fringe we are looking for. That will be x10 in this triangle, perpendicular upon hypotenuse. If we consider it just perpendicular upon base, actually tan theta is perpendicular upon base. So in this triangle the perpendicular is here and the base is this, so x10 by d, this is tan theta. Okay, now path difference, we know the path difference will be when I drop a perpendicular like this is the extra path, right? Path difference is given by this expression, also we had derived earlier, but the path difference is given by this formula. Now since we are talking about bright fringe, so this path difference should be multiple of wavelength in this manner. That means it should be n lambda, right? Now when I substitute this thing when I'll equate these two things, I'll get that path difference, which is equal to d times tan theta is equal to n lambda, right? That means tan theta is equal to, this d will go here, n lambda by 10, and this nth we are talking about 10th fringe, right? 10th order maximum. So 10 lambda by d equals 10 lambda by d, and d is given to be 1 millimeter, and this wavelength is also given. So this will be 10 times, we have to find out actually this theta. Okay, we can find out tan theta also using calculator, but here we have been asked to take it to be very small, then tan theta we can equate almost to theta, which we are interested in anyways. So this n lambda is 10 times, and lambda is 6000 angstrom, and 1 millimeter is 10 to the power 7 angstrom. 1 millimeter is 10 to the power 7 angstrom. So what we get here is 60,000 angstrom divided by 10 to the power 7 angstrom. After solving this, we will get 0.006. No wait, this is in degree. So this is 6, 2, 3, 4, 5. Let me see. This is 10 to the power 6 times 10 to the power. So 1, 2, 3, 4. 10 to the power 4. And in denominator we have 10 to the power 7. Angstrom will be cancelled because they are in ratios. So this will be 5, 6, 7, minus 3. 6 times 10 to the power minus 3. This is the angle. It will be 0.006 radian. Okay, this is the correct answer. Okay, next question is, in Young's experiment, the separation between the two slits is 0.02 centimeter. We denote by small d, which is 0.02 centimeter. Interference fringes produced due to light of wavelength. Wavelength we are using 6000 angstrom. Distance between screen and slit. Screen and slit distance is 80 centimeters. Again, for here also you can always make diagram that I used to say for earlier questions. That is always good. When we draw a diagram like this, things become very clear. But the distance between slit is small d, the capital D is 80 centimeter. Wavelength that we are using is 6000 angstrom. Distance between screen and slit is 80 centimeter. Calculate the distance of fifth bright fringe from central maximum. So from central maximum, that we know from Young's double slit experiment, at the center we will be getting zero phase difference and we will be getting bright fringe here. So from the central maxima or central bright fringe, we have to know distance of fifth bright fringe. So again, using our formula, that we know the position here, this will be d by d, and because it's bright fringe, so n lambda, right? Now this position will be, capital D is 80 centimeter, okay. Small d is 0.02 centimeter. This nth fringe is fifth fringe, and lambda is 6000 angstrom. When I'll change to centimeter, it will be 10 to the power minus 8 centimeter. So when we'll calculate all of this, we'll be getting 80 divided by 0.02, which is 4000, multiplied by 5, multiplied by 6000. Okay, that's a pretty big number, and that is 12 times 2, 3, 4, 5, 6, 7, 10 to the power 7, and then we have 10 to the power minus 8 centimeter. So it will be 12 times 10 to the power minus 1 centimeter, which is 1.2 centimeter. That means the distance of fifth bright fringe from central fringe is 1.2 centimeter. Okay. Okay. Next question. Question number 6, which is, in a Young's double slit experiment, the fringes are formed at a distance of 1 meter from double slit. Again, that means the distance between source and screen. Distance is 1 meter, and slit separation is 0.12 millimeter. Calculate distance of third order dark fringe from the central maximum. Given wavelength of light is 6000 angstrom. This, if I write in centimeter, because our answers are in centimeter, 1 meter is 100 centimeter, 0.12 millimeter is 0.012 centimeter, and this wavelength will be 6000 angstrom is 10 to the power minus 8 centimeter. Okay, now the position of third order dark fringe, this will be given by d by d 2n plus 1, we know odd multiple of lambda by 2, right? Now putting the values here, 100, 0.012, we are talking about third fringe, so 2 times 3 plus 1 multiplied by lambda, which is 6000 times 10 to the power minus 8 centimeter divided by 2. So this, keep in mind how we got, this is the path difference. We had seen the position, I'll show you, we had derived this thing in the beginning. The position, this was the relation. So the position is path difference multiplied by position is, this S2P was the path difference multiplied by capital D divided by small d. And since for depending on the fringe that we are using, if we are talking about dark fringe, then it will be, bright fringe, then the path difference is integral multiple of lambda, and if we are talking about dark fringe, then it's odd multiple of lambda by 2. Using these properties, here we are using all this formula just to recall for you people. Here we were, right? So that is what we are using here. Okay. So when I'll calculate all this, it will be 100 divided by 0.012. Okay. Multiplied by 7 divided by 2 multiplied by 6000 is 175 multiplied by 10 to the power 6 minus 8, which is 175 times 10 to the power minus 2, that means 1.75 centimeter. So the answer here is 1.575 centimeter is the distance at which we will obtain third order dark fringe from the central maxima on the screen. Okay, seventh question is, we have two slits apart by 0.0125 centimeter. That means the distance between these two slits is 0.0125 centimeters, and they are illuminated by a light of wavelength 4500 angstroms. The screen is 1 meter away from the slits. Find the separation between the second bright fringe on both sides of the central maxima. So when we have something like this, kept at a distance capital D from the screen, then we know in the center we have bright fringe, and then we have dark and bright and dark and bright. That same pattern will be formed on another side as well. That at the center there is bright, then there is dark, then bright, then dark. So in this question, so we were taking the positions from the central point to that particular dark fringe. Here we have been asked to find the separation between second bright fringe on both sides. So if this distance is second bright fringe, that means x2, then this side also it will be same x2. So the total distance, this net distance between these two, we need to find. Okay, so again using our formula of position, which we know is given by this, because we are talking about bright fringe, so this will be the path difference, and this will be on one side, on another side again the same thing. So the total path difference that I said will be addition of this much is the distance from center, another side also the distance is same, so the distance between these two fringes on either side, this delta xn will be 2 times capital D, addition of this basically. Okay, So now substituting the values, we'll get 2 times, and capital D is 1 meter. Answers are in centimeters, so I'll change it to centimeter, which is 100 centimeters. Small d is 0.0125 centimeter. We are talking about second order right fringe. Wavelength is 4500 angstrom. If I'll change it to centimeter, it will be 4500 multiplied by 10 to the power minus 8 centimeter. 10 to the power minus 8 centimeter. Okay. When we solve this, we will get 4 times 100 times 4500 divided by 0.0125, which is 14,144 multiplied by 10 to the power 6 minus 8. This is in centimeters. So this is 144 multiplied by 10 to the power minus 2 centimeters. That means 1.44 centimeters. So this B is the correct answer. Okay. Now question number 8. This is again Young's double slit experiment. So the question is, in Young's double slit experiment, the light of wavelength is given to be 6000 angstroms and is used, and obtained fringe width is 2 mm. So fringe width is given to be 2 mm. What will be the fringe width if the entire apparatus is immersed in a liquid of refractive index 1.33? Okay, so the twist here is, in case 1, we are doing this Young's double slit experiment in air. Refractive index is 1 for air. This is the given parameters. So fringe width will be, the formula for fringe width is d lambda by small d. This is for case 1. Now for case 2, what is happening is we are immersing this whole thing in a liquid, which inside a liquid which has refractive index of 1.33. Now we know something, that refractive index is ratio of speed of light in vacuum to speed of light in the medium. That means frequency, we know, remains same because it's a property of source. Frequency will remain same, but in the medium, that particular medium, the wavelength changes, right? So if the wavelength here, the wavelength was told to us was in air, now this wavelength is in this liquid, then wavelength, because we know refractive index is a function of wavelength. For different wavelength, refractive index is different of any material. So here we can see from this relation, frequency is same. That means wavelength in the liquid, okay, will be wavelength in air divided by refractive index of the medium. So we know the wavelength of source in air. Now I can find out the wavelength of the same source in this particular liquid by this formula. Okay, so here the wavelength in liquid will become wavelength in air divided by refractive index, which is 1.33. Okay, what will be the fringe width in this situation? What will be the fringe width we need to find? So the formula of fringe width, which is capital D divided by small d, and the new lambda. Okay, so here we were not given these parameters. So this is basically the old one we knew. So substituting this here, write d by d and lambda. Wait, let me write it properly. So this lambda L is lambda A. This is also lambda A. Okay. lambda A by mu. So we can see this part is the fringe width in air, right, divided by refractive index. That was 2 mm divided by refractive index, which is, so I didn't have to calculate this also. This is a easier way. So this will be 2 divided by 1.33, which is 1.503, or maybe if we have to only consider up to first decimal digit, then it will be 1.5 mm. So when this whole apparatus will be inserted in this liquid of refractive index 1.33, then the fringe width will change from 2 mm to 1.5 mm, because the refractive index is changing and thus wavelength of the light will be different. Everything is the same, only the wavelength of light will be changing, and thus the fringe width will change to 1.5 mm. So A is the correct answer. Now question number 9. If a biprism of base angle 1 degree, you recall what I had told, if we have a biprism like this, right, one prism this, one is another is this is the base, this is the angle, okay. A biprism of base angle 1 degree and refractive index of its material is 1.5. Biprism is placed at a distance of 40 cm from the illuminated slit. So we have a slit, okay, it's a single source we use actually in biprism. So this is the source of single slit, and then we'll be getting virtual sources here, right, S1 and S2. That was the intention of using Fresnel biprism anyway. So biprism is placed at a distance of 40 cm from the slit. Find fringe width at a distance of 60 cm from the biprism. Okay, distance of 60 cm. We have kept a screen and we need to find, they are interfering and forming, okay, and we need to find out fringe width at a distance of 60 cm from the biprism. Wavelength of light used is 5893 angstrom. So here we need to see one thing. If you recall, for prism, okay, so if you recall, we were talking something about angle of deviation for a prism. I told in this session again that if we have light like this, it will be deviated from its original path, and this is what we call, and in terms of refractive index and angle of prism, angle of deviation is given by mu minus 1 times angle of prism. So here this this angle is the angle of prism. Let's call it alpha, which value also we have been given. This is angle of deviation. Now the thing is, this is the light, right, emergent, and if we take it backwards, it's coming from this source, and this is the original path. So this is angle of deviation. That means this is angle of deviation. Sorry, not this angle of deviation. And if I see this particular triangle, this S1S in this particular triangle, I'll see that lambda is d over 2a. How? Because this distance of these two will be d. So distance of S1 and S will be d by 2. S1 S will be half d by 2. This is 40 centimeter, and the angle here is lambda. So using tan theta by 2, but since it's very small, we can just take this angle to be equal to this d by 2a, and since this delta is also equal to this, so when we equate these two things, we will be getting expression like this. Okay, now from here this d will be 2a times capital A multiplied by mu minus 1. This is the separation between two virtual sources, of course. Now fringe width we know is given by d lambda by small d. So we did all this because we were not given small d. So we used angle of deviation property to find out d by 2 and capital D, small d total. So from this, the capital D will be 60 plus 40, that is 100 centimeter. Wavelength is 5893. This is an angstrom. In centimeter it will be 10 to the power minus 8. And this is d lambda by d. So beta will be, this is d, this is lambda divided by small d. Divided by small d means this is nothing. Small d is 2 times, and a is what? A is, just happened, d by 2a, which is this, which is 40. This is the a I was talking about, which is 40. An angle of prism is 1 degree. 1 degree when I convert it into radians, 1 degree in radians if I want to convert, it will be 1 degree multiplied by pi by 180 degree. That means it will be pi over 180 in radians. Okay, so this will be, means mu minus 1. Refractive index is 1.5. Mu minus 1 means 1.5 minus 1 multiplied, divided by pi by 180 means 180 by pi. Then we'll solve. We need one more slide here. And I'll calculate all this by getting 100 multiplied by 5893 multiplied by 180 divided by 80 divided by 0.5 divided by 3.15. It will be 84453 something and 10 to the power minus 8. 10 to the power minus 8. 10 to the power minus 8 centimeter. This is because we converted everything in centimeter. So if I want to change it to millimeter, it will be 10 to the power minus 10 to the power. It will come out to be 0.084 if you round off millimeter. Okay. 1, 2, 3, 4, 5, 6, 7. Because in millimeter this will be 10 to the power minus 7 millimeter, and it will be 1, 2, 3, 4, 5, 6, 7.084 mm. So answer is, where is it? 0.084 mm. Okay. Next question is last question, which is inclined faces of a biprism makes angle 1 degree with the base of the prism. That is the base angle. base angle of prism is 1 degree and the refractive index of material is 1.5. Illuminated slit is 10 centimeter from the biprism. The slit is 10 centimeter from the biprism. The biprism is like this. This is the base angle. Wavelength of light used is 5900 angstrom, and the fringe width observed at a distance of 1 meter means 100 centimeter from the biprism. There is a screen where the fringe width I'm getting is, oh, we need to find it. Okay, fine. So fringe width formula we'll use, which is d lambda by d, right? Now again, this d, just now we saw this d, I can write in terms of refractive index and angle of prism like this. So this separation between slits, I can write it as 2a, this is 2a, mu minus 1 times the angle of prism. There is the separation between slit and the prism. This is okay. So D will be 2 times 10. Refractive index is 1.5 minus 1 and times angle of prism, which is 1 degree, and 1 degree we have to convert to radian, means we'll multiply by pi by 180. So this is D. So fringe width will be capital D, which is 100 plus 10, that is 110 centimeter. Wavelength is 5900 angstrom. In millimeter it will be 10 to the power minus 7 divided by all this, which is 2 times 10 times 0.5 divided by pi by 80 means 180 times pi. Then we will calculate all this. This will be cancelled. 11 multiplied by 5900 multiplied by 180 divided by 2 divided by 0.5 divided by 3.95. It will be 382 times 10 to the power minus 7 millimeter. Okay, did I do some mistake again? This was okay, this was in centimeter, this was in millimeter. If I change it to millimeter, it will be like this, and A was also in centimeter, so this will also be, then this will become 1, 2, 3, 4, 5, 6, 7. So this is fine. Even if I convert it to millimeter, these will get cancelled, and in centimeter I will get 0.372 millimeter. 2, 3, 4, 5, 6, 0.372 millimeter is the correct answer. Okay, so they were based on double slit experiment and Fresnel biprism. I hope now you can do your this week's experiment, and next week I think we have experiments like Michelson interferometer and Newton's ring, so we'll understand their theory and experiments. If you guys don't have any more questions, then we can end today's session, and I'll stop the recording.